Thank you to the organizers for inviting me to come talk about stars and for organizing this lovely weather. I am from Seattle, and so I feel right at home. It's much appreciated. It's really nice to stand here, not here, I was told, don't stand here across the line, stand here on camera and talk about stars. The last 15 years, even before the first Know Thy Star conference, have seen a real transformation in our understanding of exoplanets and stars and the relationship between them. And for people like me who have made their careers on this data, it's been a wonderful time. And I want to just start by acknowledging, is the iPad okay? I want to start by acknowledging that there are many people who are not here right now, and that many people, especially young career and minoritized folks, who are struggling in this moment. And so it's a great privilege to stand here on behalf of many people, including many who are not here right now. And so I just want to start by acknowledging the difficulty of the moment. But instead, we're going to talk about stars, and I'm going to give you the takeaway point, which is I think we should treat our stars as a different star every day. And this is where I get to lecture you about how amazing and interesting and fascinating stars are and how we need to respect them and treat them with care every time we observe them. And this is summed up, I think, nicely from what we see in the sun, which is that it is not constant in time. I think we all know this. We've all seen this in introductory astronomy classes, right? The sun, as Elizabeth said this morning, and stars, are covered in surface inhomogeneities here in the ultraviolet. They look like bright spots in the optical and the white light. They would look like dark spots. There are plage, possibly dark plage, right? There's all kinds of things on the surface that move in time. The stars themselves rotate in time, right? These are active, dynamic objects by their very definition. They are not constant in time. And so every time we observe them, we need to treat them with care. And problematically, planets go around these stars, or maybe it's a good thing. We have planets here, like one in our own solar system, around an artist's rendition. This is the motivating factor, I think, for a lot of the work in the stellar astrophysics community. We want to find these planets, or you want to find these planets, and they spend their whole lives going around these stars, which are, again, dynamic and at times turbulent objects. I don't like the word violent. They're not violent. They're just exciting. They're just very active. So when I started thinking about how to sum up this talk based on the prompt that the organizers sent me, I thought this is really a talk about what are all the ways that stellar activity can ruin your party. It can make knowing thy exoplanet really difficult. We had, again, a really nice talk this morning by Elizabeth setting the stage for star spots and related kinds of surface inhomogeneities. And how they can really mess with our ability to both detect and characterize exoplanets, both in and out of transit. But there are a great many other kinds of activity sources. Oh, there's a remote. That we need to consider, both in time scale and in amplitude. And so there are a lot of time scales at work, right? We have minutes to hours time scale effects, things that are changing rapidly on the surface, which we observe, which is going to be the focus of most of my talk. We have things that change on days to months time scale. So the sun rotates again at something like 27 days, depending on what latitude you're at. So that's right about a month time scale. And a star spot that lives multiple rotations may evolve over months time scale. And in some cases, we have measurements of star spots that are coherent and stable for decades, although it's a rare thing to measure so far. And then we know the sun varies on a year-to-year time scale, which I'll talk about at the end of my talk. The so-called activity cycle and other processes which we know and have observed in our own sun, which we are just getting hints at from other stars. There's a wide range of amplitudes. Again, Elizabeth mentioned star spot variations of 1 to sort of 3% is pretty common for low-mass stars that we see in things like Kepler and in TESS and other missions. But also sources of noise and activity, which can range up to 100% or more the brightness of the star, and we'll talk about that. These depend on stellar mass, on stellar age, on stellar evolution. There are second-order effects due to metallicity, which can cause all kinds of biases in our data. And I really tip my hat to people who, like Jesse Christensen, who work on demographic work and try to account for this. This is heroic work to try to account for demographics across these parameters. Here is a schematic diagram of that last slide. That there are lots of time scales, again, from, there we go, from minutes all the way to decades that we have to worry about. This is an incomplete census of all the effects that we might be concerned about that stars can exhibit, which will mess with your data, will ruin your exoplanet party. On the shortest time scale, again, not the only effect, but flares. This is what the meat of my talk will be about. Again, we had a really wonderful summary of star spots and related surface inhomogeneities, faculae, plage, maybe dark faculae, count faculae. On long timescales, I'll come back to this idea of activity cycles and activity variations. And I won't talk about this, but I do want us to be thinking about this. I want to plant this seed in your head that there are behaviors that we know about on stars which are on longer than decade timescales. We don't have a lot of sensitivity to this in our data right now, but this is a kind of area where I think right now there's dragons, as the old maps would say, but I think there's actually a lot of opportunity in this space. And so for the young people in the room who will go on to observe stars across many, many space telescopes and many missions, this decades to maybe century timescale is really untapped and really fascinating. And I don't have a lot to say about it today other than just say it's really neat. One of my big motivating concerns as a stellar astronomer is when I see plots like this incredible data for WASP-39b. This is amazing data, right? We have seen some of this already in slides today, where we see transits that are taken at multiple wavelengths, but also on multiple days. This is unavoidable, right? Like, you can't observe every star all the time with all the telescopes. As much as we would like to observe, what was yesterday somebody saying, trying to propose for 8 different tacks and allocations, like, it's really hard to do. And so necessarily, you sometimes have to come back the next transit and catch it with that telescope, or maybe even the next year once you've got a really great proposal and you can motivate that expensive observation. And this is sensible work, and I applaud you for doing it. But as a stellar astronomer, this is where my concern rises. Right? We saw examples of star spots coming and going, evolving, maybe even signs of differential rotation yesterday. This means that the surface is not only inhomogeneous, it is non-constant. And when you come back to it and take your exoplanet, this ignores any details of the exoplanet. When you come back to it with that same exoplanet and try to transit it and infer atmospheric properties like this, from data that expands days, weeks, sometimes years, you're looking at potentially a different star, or, to a low order, a small difference in the star. And again, the star itself, it's the same star, right? It's just going through its normal turbulent motions, turbulent activities. But when you're trying to compare whether or not this particular wiggle or that particular wiggle is well fit by your model, you have to really worry about what the star is doing on this very small level. I know that people in this room do worry about these things, but as a stellar astronomer, this is my motivating factor for worrying about this and wanting to advocate for treating the star differently every time. It's a different star every day. So transits inhabit this really obnoxious parameter space, right? The transits themselves are pretty short. They inhabit this sort of like usually hours time scale. Transits aren't that long. But we observe the transits, right? Sometimes they're on long periods, so we'll observe them month to month. And then we may have to come back years later and hope that it's still the same star, that it hasn't undergone some radical change. And so we do have to worry about all of these activity effects on all these different time scales. So the focus of my work and the focus of my talk today is on flares. And this is the best flare star, my favorite flare star. This is GJ1243. This was the most active star observed in the original Kepler mission, and this was the basis of my thesis and many other PhD theses. And it's nice when a single star can be so interesting that it motivates multiple PhD theses. This is what you like to see. These are so-called UV SETI variables, for those people who care about the old-timey variability designations. You can see 2 really interesting things going on in this star. This is like 4 or 5 days worth of data from Kepler. You can see this modulation here. This is, again, the star spots that Elizabeth was telling us about this morning. There's actually at least 2 distinct star spot groups that are long-lived on this star, which we have years of monitoring for. And then I hope it is obvious to everyone in the room, but in case you're not seeing it, there are these small little spikes, something like once an hour in this case for this M4 dwarf, this rapidly rotating M4 dwarf. There are spikes here that range from, this is about a 2% modulation, so these range from sub-percent, and in this case, this is, well, I clipped the diagram here for the plot at 20%, but it keeps going, right? This is an enormous flare, and these get produced every few days on this star, right? This is an incredibly active target. And we have senses of flares from the star in the thousands that rival basically only the sun. It's the only other star that we have enough flares that we can do the sort of statistics with as this particular target. Now, here is the sort of canonical diagram of what a flare is. I'm not going to spend a lot of time on this. But it is a magnetic reconnection event. You have magnetic fields all over the surface of your star. you'll have these loops, which we can see on the sun. I'll show you an actual picture of the sun in just a moment. There is some kind of reconnection event. Magic happens is effectively the explanation. The magic occurs, the magnetic fields get pinched or reconnect. They then send material streaming down these filaments and run into the surface. This is where the optical white light emission comes from, is the sort of impact near the photosphere. Excuse me. In some cases, in many cases, you see plasma and material launching off the surface of the star, sometimes at the exoplanet or at our planet, and these are coronal mass ejections. Okay, so here's a better view of this. This is again from the sun, from the Solar Dynamics Observatory, and kaboom. We'll let it play for another minute. This is about 3 hours of data. What I like about this animation, besides it's just very dramatic and the sun is incredible, is you get this sense once it restarts here. So we have sort of organized long field loops here, field lines. They snap, and then you can see that this field is, you can get a sense that it's actually what we call an arcade. This is not just one line, right? Not just one perfect loop like we draw in our textbooks, but it's actually this complicated arcade, this series of structures that are feeding on each other and perturbing each other, causing lots of little micro flare activity, which we'll come back to that in a minute as well. The sun is just great. Flares are, by their nature, stochastic. They're not random. I mean, they're kind of random, but they're not random per se. Random things, defy explanation. They just happen. Stochastic processes are things that are governed by underlying physics that maybe we don't understand, and so we inject randomness into our modeling of them, or into our approximations of them. But they're described by distributions. So any given flare, I can't tell you when the star starts to brighten whether or not this is going to be a small flare or a big flare. What I can tell you is if I observe many flares, they are described by some distribution. And that distribution is really important. So, right, this is really good when you care about stars. We can describe this distribution. We can describe the statistics of these. You can study them. It's really frustrating when you have an exoplanet because there's no prediction like, will the star flare today? Right? So this is akin to earthquakes. Right? Like, it's not very helpful if your house is destroyed in an earthquake and someone says, don't worry, most earthquakes are quite small. Like, that's like not very, very comforting if you've got an exoplanet transit that was incredibly expensive from JWST, let's say, and there's a big flare right in the middle of it. It's like, it's not that comforting to know that, well, most flares are actually very small. Here is the canonical flare frequency diagram. This is, again, for my favorite star, GA1243. In blue, you can see this nice, beautiful power law in log-log space, a straight line in log-log space from Kepler, thousands of flares drawing out a very perfect power law, some argument about whether or not this is real. Probably it's not. Probably this is just statistical noise. We see this star was reobserved by TESS about a decade later, and you can see that it follows the same power law, so nothing has changed. It's effectively behaving the same. So even though the star is very dynamic, the statistics that drive that process are effectively the same. And there's error bars in both directions because there's error bars in how well we can measure things, and there's error bars in the statistics of recovering them. And so these are kind of obnoxious distributions to fit, but it's doable. This power law governs how we think about flares. Now, flares themselves have been described nicely by smooth models. This is a beautiful model by my recent graduate student, Lupita Tovar Mendoza, who many of you may know. She took hundreds of these flares and aligned them, right? So we have 1 minute cadence, which is good. You can see a lot of structure in the flare. You can clearly see the rise and the decay. But 1 minute cadence is still actually quite slow. But when you take hundreds of these things and you align them, you can actually get a higher time resolution. And so this is what Lupita did. And you get this nice, beautiful curve. We fit this here with this sort of convolved double exponential and a Gaussian, and you get this really nice model. This has been a super useful model for describing flares and very precisely removing them from transits. There are a lot of second-order effects, and so I'm going to plug Ward Howard's talk tomorrow, which will talk about a lot of these effects and taking this to an actual precision regime across wavelengths. But this common profile has been really useful and widely adopted in terms of removing flares from exoplanet data. Now, we did this in Kepler as well earlier on, and we could show that some flares were very complex, so-called complex flares, multi-peak events. And another plug for Ward Howard's paper from 2022 is that essentially all flares, if you look at them carefully enough, are complex. And this goes back to that picture of the sun, that it's not just a single loop snapping and creating one flare event, right? The sun is a chaotic, dynamic, turbulent environment. And so one flare is likely to be involved in a very complex active region, causing lots of little subflares and lots of little perturbations. And so when you look at high enough time cadence, every flare is actually complex. There are no simple classical flares. So we have to just reckon with this when we're describing them, describing the energetics and describing the impacts on planets and their characterizations, that the flares are actually very complicated objects. And flares have been a pernicious problem for exoplanets, I think is a fair statement. Here is a lovely summary for AU-MIC from Emily Gilbert's paper a couple years ago, just looking at, I think this is all test data from AU-MIC, looking at transits just from AU-MIC-B, just from one of the better resolved planet in this case, just looking at 5 transits just from the test data that are impacted by flares. Now this is an active young M-dwarf, so it has lots of flares all the time, and so by even statistics you would assume that there are flares during the transits, and that's what we see. These can be a huge problem for modeling, especially if you have a long period, right? If you have a very active star with lots of flares and very few transits, like in a long orbital period, then you're going to have a hard time recovering the transits, just like in the case of the star spots. But also, even in cases where you have lots of transits, the flares can really mess with your ability to measure the ingress and the egress times that are very important for, say, transit timing measurements. The impact here can be devastating. So when you have large flares like this that happen right at or overlap the egress, for example, here somewhat in ingress, egress again, this causes a lot of uncertainty if you're trying to infer the position of other planets by the perturbations in the transit times. Flares can be a huge problem, and this has been a lot of use for this model of sort of flare morphology model, trying to accurately remove the flares so we can still jointly model the planets. In the same way of modeling the transits and the star spots, you also need to model the transits and the star spots and the flares. Now, talking about free parameters in our models, every single flare is governed by some amplitude and time scale and centering time. This introduces a ton of free parameters in your model. It becomes very hard to do if you need to fit hundreds or thousands of flares even. Again, it's not that comforting to know that, well, most of them that you can't see are small. Flares occur across wavelength. So here is a great figure from about 13 years ago from Ben Tofflemeyer's paper looking for infrared flares. This is how we used to do flare observations in the good old days. You would just stare at a star and hope it flared, which breeds a level of sort of superstition in how you become an observer, right? You have to listen to certain music and eat certain snacks at night to hope to will the star to flare because you're just sitting there waiting. It's much better now. We have exoplanet transiting telescopes that stare at the stars for us. But in the old days, we would stare at them with maybe multi-wavelength imagers. And so Ben's got this great plot here of like multiple flares, and you can see they're very bright. Flares are hot events. They have characteristic equivalent or effective temperatures around 10,000 degrees, though we'll talk about that. And so that means hot flares on predominantly cool objects. They stand out in the blue. So right, this is a 1.5 magnitude flare in the U band, which means it has about 1/4 of magnitude in the G band. By the time you get to the I band, it's barely detectable. And Ben was looking at the same time at J, H, and K, and from the ground, it's not resolvable. You can't see it. There's too much noise in the atmosphere. But from space, stars flare in the infrared. And so here is a now famous example of TRAPPIST-1, the best exoplanet system, right? It has, right, transits impacted by large flares. Here's a K2 observation, right, big flare right on top of transit. And then here is Spitzer data, a complex flare right up against the ingress of this transit. And I don't know what to make of this little bump here, or this little dip here. Flares in the infrared are actually a big problem. I am not on any JWST proposals right now, but there are people in the room who are. And so I would encourage you to talk to them if you have been observing TRAPPIST with this instrument. I'm going to bet $1 that you have flares in your infrared data, because some of you have showed them to me, and they're amazing, and there's lots of physics we can do with them, but they are a huge problem, and they're going to be a huge limitation. These things overlap transits, and they cause all kinds of strange noise characteristics in our data. Now, it would be nice to take the statistics we have in the optical, where the flares are high amplitude and easy to describe, and just project them into the infrared. Again, it's not very comforting to know that most flares are small, but at least when you have a flare, it'd be nice to be able to remove it from our infrared data with some reliability. And one of the challenges has been we don't have a robust model for what the flares look like at different wavelengths, even between optical and infrared. And this is because the canonical flare temperature of around 10,000 degree Kelvin is a gross simplification, and flare astronomers hate this. It's a pet peeve of ours when people say, just the flare is 10,000 degrees, because that's like obviously not true. Go back to this diagram, there's lots of non-thermal processes, right? It emits all these other wavelengths, but also the flare is a dynamic process, right? It has a hot peak, and then it has a cooling phase, right? There's a teapot cooling phase where it comes back into equilibrium with the photosphere. So when we measure an effective temperature for the whole event, we're averaging over the whole event, right? The flares change color rapidly and dramatically throughout the event. And one of the tricks that has been confounding us right now is that even describing them as one average temperature across the event is not sufficient when we're talking about looking in the infrared, because flares look overly bright and cool in the infrared. So again, there's been interesting papers here from Moss and from Howard looking at JWST and infrared flares, and they're cooler than we expect. This is a hot area of research, excuse the pun. All right, flares are a problem. Let's go to long time scales. The sun is a dynamic object on long time scales, like we said. Here is the famous butterfly diagram, a nice illustration from Brett Morris's paper, showing the emergence and decay of stellar activity as shown by star spots, but is also followed by flares. Here is that same kind of diagram just for one solar activity cycle from maximum to minimum about 20 years ago. And here is the flare frequency distribution, or the cumulative distribution of flares in these sort of 1 month bins. And you can see the flare activity, the sort of specific flare rate, changes by 2 orders of magnitude from active maximum to active minimum. This makes flares one of the best measurements of stellar activity cycles, in fact. But also contributes to the concern that if you were to observe a star looking for an exoplanet here and here, you would get substantially different noise properties in your data. So we've been looking for this. We've been trying to find these kinds of examples. Here is a nice example from TESS that we found a few years ago. This is an M3 star. An active star, it's burbling along. There are flares guiding the eye, and they're in orange. We put the orange on there, obviously. And then 1 month, TESS observed it, no big flares. This stood out as being unusual. And then it came back a few months later, and big flares, and on it goes. This was really curious. And so we went back to the Kepler data. My student Tobin Wayner just submitted a paper this last year about this. You can see that in Kepler, this star had a relatively stable flare rate. This is the sort of power law intercept. There is 1 month of Kepler, or one cycle, sector, whatever the name we used back in the day was, or one chunk of Kepler data, quarter, that was the one, where it was a little bit low, but like it's fine. And then we come back to TESS. The error bars are bigger because we have smaller windows of time. And we do have this 1 month that is abnormally low. And then because we're scientists, we're going to call it sort of an outlier, but it's 2.7 sigma. So it's obnoxious, but not statistically significant. So it's like personally significant. This is one that we want to come back and monitor again, right? This is a star that is like my favorite star, not showing really coherent slow variations like we would assume we would see on the sun. But we may be seeing some quiet months. There may be periods of quiet and periods of activity. So even on a month-to-month and then year-to-year time scale, this star may be behaving differently. And a plug that we haven't talked a lot about is the decade timescale coming from missions like Gaia. Now, we have the Kepler test baseline, which is already 15 years, but Gaia, RIP, just shut down after 10 years of observation. And what it provides in its upcoming DR4 data release in the fuzzy future will be a decade timescale of almost exoplanet precision, where you can see stars slowly changing in brightness. Now, these are 2 flare objects that I picked out from the Gaia alerts, where we have some preview of this time series. And you can see there are small perturbations. Now, this one is a known binary system, so whatever, binary stars are weird, or they're great, depending on who you ask. This one is apparently a single star, or it has no obvious binarity, and you can see a small change in the brightness. Is this an activity cycle? Is this some sort of chaotic process that we yet don't understand on a decade timescale? I don't know. But again, this is a revolution, especially in concert with missions like TESS, which we'll observe forever, I'm sure. And so at last, my recommendations for you. If you are observing a star, treat it like a beautiful, bespoke object every time you observe it. Get lots of calibration data, especially in the optical. If you're observing that faint infrared target with a $10 billion telescope, go get a 1-meter telescope on the ground for relatively cheap and observe it in the G or the U band at the same time to try to measure these flares. They will be very helpful in disentangling the mysteries you find in the infrared. When you do observe them, use high time cadence if possible, particularly when you're observing in the optical. Go at that high time cadence because the flare structure may be quite complex. And if you really care about transit, ingress, and egress, these timescales are really important. Get calibration data, especially out of transit. We heard about in versus out of transit scatter, but also the star spot modulations can vary over time. Get long baselines around your transits. I know this is expensive, but get baseline as much as you can to describe the noise of the star around the transit. Single transits are great, especially with JWST, because you can assume the star is relatively the same star in one day, although, again, it is inhomogeneous across its surface. And many transits are good because you can marginalize over stellar variability. All right, in my last negative 15 seconds, I was at Know Thy Star 1, and I showed this. This is my summary then, and we talked about flare rates then. So here are my predictions for Know Thy Star 3. I don't know if the SOC is planning 2032 as the date, but extrapolating periodically like we do in exoplanet land, I assume that's when it'll be. JWST will have just reached the 10-year milestone. My predictions are that CMEs and flares impacting exoplanets will be a discussion point, that Know Thy Planet, Know Thy Star will be a hot area of research. We've heard about this from the exoplanets, but also in the flare regime now. And that my hope upon hopes, is that long timescale behavior between these missions will be a major focus. And so I charge you, the young people in this room, to go make this a reality so that I am not proven a fool in 7.5 years. Thank you.
Great, lots of questions. I don't know who's grad student. Are you a grad student? Yes, please.
And you get a pencil, right?
Yeah, come on.
Hello?
Hello.
I want the pencil. Yes. So, Sebastián Carrasco of New York State University. Can you use high cadence spectroscopy to see if there are any activity variations, like in H alpha, H beta, and the calcium lines? Does it show any correlation?
Yes, yeah, you can definitely use high cadence spectroscopy. It's just expensive, it's hard, and you go back to this sort of superstitious era of pointing your telescope at it and just praying that it flares. And so if you have the availability, yes, point a spectrograph at an M dwarf and just watch for it to be changing. But
I have a telescope.
Yeah, but it is expensive in both time and in personal impact when it doesn't flare.
Okay, thank you.
Yeah.
Hi, I'm Aurora Kessley at IPAC. I was wondering if there's been any evidence or if we expect activity cycles on the latest M dwarfs like M8s. Have we seen anything like that yet?
So there have been some long-term like calcium monitoring campaigns which have gone into the early M's, have not been able to go into the late M's. So my feeling is it is totally under constrained. There are reasons to believe that they would not have started, that the stars have not reached that phase in their evolution. They're still fully saturated. They're rapidly rotating, even if that's at 110 days or whatever. But they're still very dynamic and turbulent, and solid body. There's not a lot of differential rotation, for example, which might drive and govern these timescales. So there's reasons to believe there's not, but it is like an open question. When do activity cycles emerge? At what times? At what masses? How long do they exist for? I think we effectively don't know anything. Somebody call me out on this, but I feel like we effectively don't know that much about statistically when these things happen.
Maybe one more, right in the middle.
This is good. This is my program officer who is funding a grant on this work. I didn't acknowledge my NASA grant, and I apologize.
It's entirely fine.
I want to change my slides real quick.
This is Joshua Pepper from NASA headquarters. I really want to ask about the first bold-faced bullet you've got there. If we're observing a different star every single time we observe it, should we be talking to each other about the stars that the planets are orbiting with respect every single measurement of the star to have the accompanying epoch of that observation embedded in every paper, every online database, every archive? How can we better characterize the time-changing nature of stars as we talk to each other about this?
Well, we need to follow the lead of certain organizations in making open data the standard. Certainly, that's helpful. The accompanying part of this is, of course, models. When we interpret these with atmosphere models, for example, those need to be included as well, and we should model the star jointly every single time. Again, that's very expensive, as others said. You can't model the whole star as an inhomogeneous surface at every epoch of your data. That's very expensive. But we do need to make sure that these are reproducible, and then, I don't know, get smarter people than me to model the stars, I think is the answer.
One last one, very, very
Hi, I was wondering, are more spotted stars flaring more? Is there any sort of relation between flare rate and how spotted the star is?
And what was the last part? Flare rate and?
How spotted and
Oh,
and the flare rate,
spottedness, yeah. Right, so akin to the question earlier today about whether or not spot amplitudes and spot periods are correlated, flares and spots are troublingly uncorrelated in our data often. There is some, again, weak correlation. On the sun, you see the flares happening near or around the spot, sometimes at the same location of the spots. What we see on these active M dwarfs, like the best one up here, is there is no phase information. The flares happen randomly with respect to rotation phase. And we do not yet have good examples that I have seen of changes in flare behavior and changes in spot behavior. That's not to say that we won't find them. Again, when we look at decades time scale, maybe not. This is going to go back to your point about whether or not we see this in the stars. These are primarily the young stars, where they are fully saturated, rapidly rotating. So again, there's reasons to believe we won't see lots of changes, but in the M dwarfs, maybe not, but in the K dwarfs, maybe. Yeah. Thank you.